Hello children, now we'll see chapter 10, mechanical properties of fluids. See in this chapter we are going to learn about the common physical properties of liquids and gaseous. So the liquids and gaseous can flow, and that's why we are calling it as the fluids. So we are telling that mechanical properties of fluids, all that we are going to learn through this chapter. So due to this property only we are telling that and distinguish the liquids and gases from the solids in a basic way. As we know that fluids are everywhere around us, right? So earth has an envelope of air and 2/3 of its water, as we know very well. So water is not only necessary for our existence, right? Every mammalian constitute mostly of water in their body. All the processing occur in living beings, including plants, or medicated by fluids, right? So to understanding the behavior and the properties of fluids is very important, right? So how can we differ the fluids from solids, and what is common in liquids and gaseous? Let us see in detail, right? So unlike a solid, a fluid has no definite shape of its own, right? Solids and liquids have a fixed volume, whereas a gas fills the entire volume of its container, right? Volume of the solids can be changed by stress, right? The volume of solid, liquid, gas, all the three matter depends on the stress, or we can call it as the pressure acting on it, right? When we talk about the fixed volume of solid or liquid, its volume under the atmospheric pressure. See, the difference between the gaseous and our solids or liquid is that for solids or liquids, the change in volume due to the change of external pressure is rather small. In other words, we can say that the solids and liquids have much lower compressibility as compared to the gases. See, fluids are the substances which can flow, right? So examples, we said that the liquids and gases, and the point we said about the pressure. When an object is submerged in a liquid at rest, the fluid exerts a pressure or a force. We can say the term a force on its surface normally. So you must understood and analyze this statement. The fluid exerts a force on its surface normally. That is, we are calling it as thrust. For examples, a sharp needle, when pressed against a skin or any other material, what will happen? It will get pierced and remain its interact, or when a blend object with a wider area. Think about the difference between the both, about the pressure. When the teachers introduced pressure from the lower classes, they may given a lot of examples like this. Because of you have to understand that the pressure how act depending on the area, right? And you may take like some of the examples in the everyday experiences. It gives the convenience, both the force and its coverage area is very important, right? Smaller the area means on which the force acts, greater is the impact. This concept only we are telling that pressure. What we said, when an object is submerged in a liquid at rest, the fluid exerts a force on its surface normal. That means there where the component of force, this is not parallel to that. If suppose it's exert a pressure on the fluid parallel to that, the consequence of Newton's third law, right? This force will cause the fluid to flow parallel to the surface. So the fluid is at rest. It cannot be happened. The parallel force cannot be happened. So that the force exerted by the fluid at rest, that has to be perpendicular. That has to be normal to the surface, right? So the thrust experienced per unit area of the surface of a liquid at rest, we call it as a pressure, P, which is equal to force per unit area, and the CG is dyne per centimeter square. The SI unit pressure is Pascal, or we can say that Newton per meter square. This and all from the lower classes you are studying. 1 Pascal, which is equal to 1 Newton per meter square. Right. Liquid in equilibrium. If suppose the liquid is in that equilibrium, that is the rest condition, what will happen? See the container in a vessel. It's an equilibrium state of at rest. The liquid at rest. Suppose the liquid exerts a force F on the bottom of the surface in an inclined direction, that is OA. So the surface exerts an equal reaction R to the water along OB. Right. So the reaction R along OB, that has two rectangular components. You have to take the two rectangular components, x-axis and the y-axis. So one we can take it as the tangential component. So the tangential component which is here is what means OC. OC direction is the tangential component. That we can take it as the R cos theta. And that OD direction, that you are seeing, that is normal component. That we can take it as R sin theta. So the liquid cannot resist any tangential force. So that the liquid near O, that should have the flow along OC. So suppose liquid at rest, the force along OC must be 0. Because parallel must be 0 at rest. Right. So R cos theta is 0. Then R, which is not equal to 0, right? R cos theta is 0. So cos theta 0 means theta which is 90 degree. Obviously, we can understood from this example, the liquid always exerts the force perpendicular to the surface, right? At every point. So this is the base point for all the different phenomena which you are going to learn in this chapter, right? So what is the measurement of fluid pressure? With this example, you can understand that. See the diagram. This helps to know the measurement of fluid pressure. This is a small pressure measuring device which is placed in a fluid-filled vessel. This pressure sensor, which is consists of a small pistol, area we can take it del A. See, the cylinder which is evacuated and the spring is calibrated to measure the force acting on that. Now, the inward force exerted by the fluid on the pistol will be balanced by the outward spring force. By this, we can easily measure the pressure. Got it? How we are measuring it. Right. So the magnitude del F, if we taken the magnitude of the normal force acting on it, the pistol against the pistol over the area is what we said, del A. Yes. So the fluid pressure P, we can say that what? F by A. So here we have to take the del F by del A. So limit del A turns to 0. Del F by del A we can take it. By calculating this changing in the force per unit area, we can get the pressure, particular pressure. You can see, as we already studied about the density many times, here this is one of the dimension, or we can say the phenomenon to know about the fluid pressure, right? This is one of the another quantity we can say that is indispensable in describing the fluids. So the density we can say notate or denoted by rho. For a fluid of mass m, which is occupying the volume V, we can say that then the rho, which is equal to m by V. The dimensions of the density we can say m L power minus 3. The SI unit is kilogram per meter cube or kilogram meter power minus 3. So it is a positive scalar quantity actually. And we can take a liquid is largely incompressible and its density is therefore we can take at all the pressure, right? So for the large variations of density with pressure we can take it. And Pascal's law. See, Pascal's, which has given the transmission of liquids or transmission of fluids pressure. He has given and given the proof, theoretical proof for the transmission of fluid pressure. So according to Pascal's law, the pressure applied to an enclosed liquid is transmitted undiminished to every portion of the liquid and the walls of the containing vessel. We'll analyze the statement. See what it stated that the pressure exerted at any point on an enclosed liquid is transmitted equally in all the directions. Right. The pressure in a fluid at rest is same at all the points. That is only they said. See the container containing liquid. We can consider a small element ABC and DEF, which is in the form of a right angled prism. We can imagine that the interior of the fluid at rest. Right. So the element is very so small and all its part can be assumed to be the same depth of the liquid. Then only we can take the effect of gravity is small at all the points, right? Suppose the fluid exerts the pressure PA, we have taken PA, PB, PC on the phases, see the phases BEFC. See the dotted line also you have to consider BEFC, that is one side, that one phase we have taken, and ADFC, another phase, and ADEB. So it is the force which is applied on that we can say FA, FB and FC. Against the area AA, AB and AC we have taken this and all. Now for the equilibrium of the fluid, we have taken the triangle ABC, the angle ACB which is equal to theta. So by taking the angle ACB, the theta C we have taken means along the horizontal direction when we taken, then FB sin theta which is equal to FC side. See the FC opposite. So sin theta opposite side. So FB sin theta which is equal to FC. Got it? Now the vertical direction is what? FB cos theta which is equal to FA. Is it right? So now we have taken the from the above equation pressure. Pressure is what? Force per unit area. So pressure force per unit area for the horizontal direction is FB sin theta by AB sin theta which is equal to FC by AC. And for the vertical direction, yes, FB cos theta by AB cos theta. So that is equal to FA by AA. So pressure on A, that means side, every face is equal. FA by A, FB by B and FC by C, that means AC, area of C, side C. So pressure PA which is equal to PB which is equal to PC. So from the above expression you may understand that the pressure exerted in same in all the direction in a fluid at rest. So this proved by Pascal's law of transmission of fluid pressure, right?